Okay, let's just jump right into this. You probably opened it this morning, grabbed some milk for your coffee, and didn't give it a second thought. I'm talking about your refrigerator. But in this explainer, I really want you to start looking at that common household fridge not just as a boring appliance, but as an absolute, bona fide magic trick of physics. Literally, it is a continuous, looping thermodynamic miracle happening right there in your kitchen. And honestly, the best part? The science behind this grand illusion is something absolutely anyone can understand.
But okay, to really get how this magic trick works, we have to kind of throw out our basic assumptions. Think about it. When you open the freezer door, you feel that blast of chilly air hit your face, right? It feels exactly like the machine is manufacturing cold air and just pumping it into the box. But here is the mind-bending truth. You actually cannot make cold. Cold isn't a physical thing you can just whip up in a factory. Cold is simply the absence of heat. And that brings us to this foundational rule. It's basically the ultimate mantra of the entire heating and cooling industry. You can't make cold, you can just remove heat. So your refrigerator, it doesn't pump cold air in, not at all. Instead, it acts like a giant thermal sponge, constantly soaking up the heat energy from your groceries and then pumping that heat out into your kitchen. It is literally just a heat relocation machine.
Now, you might be wondering, why does mastering this little trick of removing heat even matter so much? Well, let's talk about the number 3. If you just leave a glass of milk out on the counter at regular room temperature, bacteria starts throwing a party and can spoil it in just 3 hours. 3 hours. By actively pulling the heat out of that milk and keeping the space perfectly chilled, we drastically slow down that bacterial growth. We're extending the life of our food from mere hours to weeks. And hey, if we remove enough heat to actually freeze it, we stop the bacteria entirely. So how exactly do we actually pull this heat out? Well, it all comes down to a principle called evaporative cooling. And I guarantee you've experienced this firsthand. When you put a little rubbing alcohol on your skin and it feels instantly freezing? That's not because the alcohol itself is actually cold. It's because the alcohol is evaporating. It's turning from a liquid into a gas. And to make that phase change happen, it has to steal heat energy from somewhere, and it steals it right from the surface of your skin.
The brilliant secret behind your fridge is that we use a highly specialized chemical to do exactly what that rubbing alcohol does, but on a massive, endless loop. We call this the refrigerant. It's a fluid specifically engineered to have a ridiculously low boiling point. We're talking sometimes between 4 to 10 degrees Celsius. Because its boiling point is so incredibly low, it can easily flip back and forth from a liquid to a gas. It endlessly loops through the system, acting exactly like a chemical sponge to absorb and release heat.
And to keep this refrigerant looping continuously, we rely on a specific set of tools. Think of these as our cast of characters. They each have a very specific, absolutely crucial job. We've got the compressor, the condenser, the expansion valve, and the evaporator. Together, these 4 guys create the closed, continuous circuit that we call the refrigeration cycle. What's really cool about this roadmap is how clearly it lays out the journey. You can see it's a completely closed loop. That refrigerant never actually leaves the pipes, it just constantly changes states. We are going to trace this exact path step by step, starting right over on the right side with the true beating heart of the whole system, the compressor.
So the compressor is exactly what it sounds like. It is the squeezer. It's a motor-driven pump that breathes in the low-pressure refrigerant gas and just squeezes it as tight as it can. Now, the laws of physics dictate that when you compress a gas, you drastically raise its temperature. If you've ever frantically used a manual bicycle pump and noticed the metal tube getting super hot in your hands, you've witnessed this firsthand. The compressor squeezes the refrigerant until it becomes a high-pressure, superheated gas, way hotter than the regular air in your kitchen. Next up, this superheated gas flows into the condenser. These are those crazy snaking coils you always see on the back or tucked underneath your fridge. Because the gas inside these coils is now much hotter than the room's air, the heat naturally flows out of the pipes and into your kitchen. Actually, this is exactly why the back or bottom of your fridge always feels warm to the touch. So, as it dumps this heat outward, the gas cools down and condenses back into a high-pressure liquid.
Okay, so now we have a warm, high-pressure liquid. But remember, we need it to be freezing cold to do its job. Enter the expansion valve, sometimes called a capillary tube. This is our relaxer. It's basically this tiny, super narrow restriction in the piping. When that high-pressure liquid is forced through this tiny little hole into a much larger area on the other side, the pressure drops instantly. This sudden, violent relaxation causes the temperature of the liquid to absolutely plummet, turning it into a freezing cold, low-pressure mixture.
And that brings us to the evaporator. This freezing cold liquid now enters the coils inside the actual main cabinet of your fridge. Because this liquid is so much colder than, say, your leftover pizza or your fresh milk, the heat from your food literally rushes into the refrigerant. Remember that super low boiling point we talked about? As the refrigerant absorbs your food's heat, it literally boils right there inside the pipes, turning back into a gas. See, boiling doesn't always mean hot. By boiling, it has successfully stolen the heat right out of your groceries.
Just to guarantee this makes total, absolute sense, let's look at the ultimate analogy. Think of the refrigerant as a sponge and the heat as water. The compressor squeezes the sponge super tight, wringing out the heat into your kitchen. The expansion valve allows that tight sponge to suddenly release and relax. Then, that relaxed, perfectly dry sponge goes inside the fridge, the evaporator, where it can easily soak up all the heat from your food. Squeeze, release, soak. Over and over and over again.
Okay, let's pivot for a second, because here is where the physics gets incredibly cool. We've got an amazing encore trick for you. Everything we just talked about, it requires a big electric motor to run that compressor. But what if you're entirely off the grid? What if you're in a remote cabin or out in an RV and you have no reliable electricity to squeeze that gas? Can you still make a refrigerator work?
The answer is a resounding yes, and it's all thanks to something called an absorption refrigerator. Let's compare the two real quick. Your standard fridge at home uses an electric motor. It has a bunch of moving parts, and you can always hear it humming on and off in the background. An absorption fridge, on the other hand, completely tosses out the mechanical compressor. It is powered purely by a heat source. It has literally zero moving parts, and because of that, it operates in total, absolute silence.
Now you're probably thinking, how on earth do you pump a gas without a motor? Well, the absorption magic relies on this brilliant chemical workaround. Instead of just one single refrigerant, it uses a clever mixture of ammonia, water, and hydrogen gas. You just apply a tiny amount of heat, like from a small propane flame to a boiler. This heat basically boils the ammonia right out of the water. The ammonia gas rises, cools, and then mixes with the hydrogen, which drops its pressure, allowing it to evaporate and absorb heat from the fridge, completely silently. It is genius, and it's exactly why these are the absolute gold standard for RVs and campers.
And this incredible workaround shows just how adaptable this technology is out in the real world. A while back at a TED conference, a researcher named Adam Grozer presented an idea for a portable absorption fridge for the developing world. The idea was, by placing a small, sealed unit over a simple campfire to act as the heat source, the resulting chemical reaction can cool 15 liters of water, that's a lot of water, to just above freezing for a full 24 hours. That means you can safely store life-saving vaccines in incredibly remote villages, using nothing but the heat of a literal fire to create cold.
So from a mechanical motor loudly humming in your kitchen, to a silent campfire protecting vaccines in a remote village, the magic trick of removing heat is honestly one of the most vital, foundational technologies of our modern world, and it all just comes down to controlling pressure and taking advantage of evaporation. So I'll leave you with this to ponder. If we can use the roaring heat of a campfire to keep a life-saving vaccine perfectly chilled, what other massive global problems could we solve just by harnessing this simple silent magic of thermodynamics?